Okay, guys, and this is actually not just for the NATS students. I realize this video will be good for Physics 1200 as well. So this is the analysis of the dice data. And if we look at the manual here for NATS, let's make it a little bigger so it's easy for everybody to read. There we go. So count the total number of dice in the undecayed bucket. So we need a start number, and you should have gotten 300. Okay. Throw the bucket of dice into the drawer. We did it on the table in NATS. And count the number of sixes that have decayed, and then move them into the decayed bucket, so that you don't have them in the main bucket anymore. And now you throw it again, and it says repeat that 8 times for a total of 8 times. Okay, so I have quite a few here. Let's see. Well, that's 8, right? So we basically are going to be talking about this one here, and I'll just emphasize it. Tick outside border. Here it is. So you should have something like this. You've put down the start number, and you have the count that you made for the number of throws. Right? So you would have this and this to start with. Now, it says here to make a paper graph, and we don't need to do that. We can just make on an Excel, like it says in Part C. And it says to plot both the number you decayed and the number that are left. So we need to know what that is. So we set this equal to this, the one before it, minus the number of ones we removed, the number of sixes. And by the way, I do remember seeing some people's data where they used a different number each throw, and that's actually not the end of the world. Okay, let's see here. So that changed slightly, but that's because, well, I had some artificial data here, and now I have it all set up the right way. Okay, pause for a sec. I'm back. Alright, so we have the number left, and now we also want error bars, and error bar for a counting experiment is always square root of the count. Okay. So now, oops. And so we do square root, and then enter, and it's square root of the one next to it. Oh, excuse me. And then we use our fill handle. There it is. Okay, so we need to plot this. This one, well, let's see. I don't know if this is going to work out. Oh, I know what to do. We can just play a game with Excel on Excel for a minute. Let's just put 50 here for the time being. And then, because I had trouble with it a moment ago. So an insert, now it said to connect the dots, but you shouldn't do that. And yeah, there it goes, it worked. And we can just get rid of this. And great, so now we have, because there's no such data point for throw before we started, so that's why we leave this one blank. Sweet. And now we can add error bars for the number of sixes. And first of all, we need to double click here, click, and you see this pops up. Now Mac users don't get this drop down box here, right? So you have to do is go up here to format, see how it changes, and then here is where you can pick it up to choose something to edit. In fact, what we need to do is to actually add something. And here's something that'll save you some time. Before you add the chart element, just click once. See how the number of sixes, the dots all highlight. Sometimes if you don't get it right, only one dot highlights, and that, just watch out for that, because if that happens, you'll go through some formatting and then you'll say, oh gosh, I gotta go back and do it again. Now I'm going to add a chart element, and reason I selected it is because if I don't pick one of the data series, it'll put error bars on both of them, and then I have to go back and remove them from the one up here. I suppose, strictly speaking, they could have error bars, but since it's just a difference between one, you could put error bars on them, but for us right now, this is our data, so we'll go back and we'll add the error bars. So again, you guys with Macs won't have the drop down box here, so you click up here, design, format, and what happened to error bars? Not there. Interesting. Let's see if now they'll appear. So I'm not sure what to do here. Let's try one more time. What I did is I clicked off the chart and I brought the chart back to the forefront, and lo and behold, and give it a little tickle. You click on this icon here, that's the bar graph. So for the X error bars, notice that's what we picked up here in the upper left. I want a fixed value of 0. And now for the Y error bars, we have custom, and we use our square roots that we created. We have to click this arrow first. Bingo. And now we click it again, plus minus. And it's perfectly okay to, so now there's the error bars. So one could insert here, and we could give it a plus minus, and you have to hit this apostrophe first, because if you don't, Excel will complain. See, plus minus number left, and you see Excel complains because it thinks it's a formula, so I just have to add an apostrophe. There we go. And so that's equal to square root. Yeah, I don't know. I'm troubled by this. I don't think that you should do this. It's a little different too. You see, what happens is that you wouldn't normally do this, because when a real radioactivity, you wouldn't know how many nuclei are left. You would only know the count, you see. But we'll follow the directions. Okay, so now what we need to do is we have to add trend lines, because that's what the directions say to do. Plot them. Have the computer find and plot an exponential trend line and print the equations of the on the graph. Okay, and then which numbers give the original t equals 0 count, and which tell you the decay constant. Okay, let's go for it. So if we take a look over here, this is interesting too. Look at that, 300, 149. So we already have our half-life there. But let's highlight the graph, design, add chart element. So we need a trend line for the number of the number left, and we need a trend line for, and it's exponential, for the number of sixes. Bingo. There it is. Here's our legend. And we can clean that up. Well, it's up to you, personal taste. Okay, I like to put a white background so that way I don't have the grid lines showing through. And make it a little bigger, maybe easier to read, and that can be done, but you guys, I'll leave the jazzing up to you guys. Alright, so now we need we want to display the equations. So if I just have this going on, and remember this sidebar here, to make it appear, you have to go click, and then for Mac users, see up here, design format. So we want to do the trend line for series 1. I wonder why. Oh, series 6s, number of 6s. And so once again, the bar graph and the number of 6s I think we're working on. Yep. So then we want to display the equation and display the r squared value. And we can move that around. And I'm going to make that a little bit easier to read. And part of that would be to set a fill here. And then I'm also going to put a box around it that's the same color as the data points in the trend line, so it's very obvious. Okay. Now let's format this trend line. And if we had this thing already up, you notice when I clicked on the trend line, the option showed up. So we have our equation here. And, you know, in my opinion, you can set the intercept and it would be 300 because you know it. There's other ideas that go with this, but we're just going to do basically by the book, what the lab manual told us to do. And once again, I'll make the type a little bigger so it's easier to read. And back to format, I'll put a white background once again, and I'll make the outline match the color of the data points and the trend line itself. Okay, pretty nifty, huh? So this thing could use axis labels, axis titles, so this would be throw number, or you could even say it's time, t equals 1, 2, 3, 4, 5, 6, 7, 8 seconds, and then this is number of dice. And then you have the legend to tell people what's being plotted there. Excuse me. Now, let's see now. One thing we see that we have a half-life here of approximately 4 seconds. And as a prediction we can make just from the graph, because you see at plot 0, at time 0 we have 300, and at time 4 we have 149 left. And let's see how that compares to what the manual says. Alright, so our value for lambda is supposed to be 0.1823, and we get 0.1823. 0.172. Not so bad. Let's see what happens if we let this thing choose the intercept for us. So it got a little worse. So it's a toss-up. I personally think you can keep it there because that's a known data point. So there's different ways of setting this up to deal with like I was doing here, which is more advanced than the what we did, and I included in a way to set the total number of dice, and it just is way above NATS 1010. So I just wanted to keep it simpler for you. So notice here now, here's our fit equation, and copy. Let's bring it forward, and let's paste it. So, and this is what the trend line is giving us, and x happens to be the throw number, and lambda is the coefficient 0.172. Now, I'm not quite sure why they wanted us to plot down below here, but it's the above one here that counts, and you see n sub 0, that is the 300, and this comes out of the math. This is calculus. When the number of if the amount of the number we see for every given second is dependent upon the number that are there, lambda n. This is why we end up with this exponent equation. And that's a classic calculus thing. And then looking for the half-life, we set n equal to 1/2, I believe, or 1/2 n sub 0, of course, excuse me. There it is. And we can come up with this 0.693t. Oh, excuse me. No, that's how we can figure out what tau is. So in our case, tau, we figured it out roughly to be 4. But let's see, in my case, don't forget, maybe not your case, but this lambda is the decay constant, and here it's 0.1823. And yeah, you would have expected it to be, if it's number of 6s, or any one number, it doesn't matter. It could be, since all the dice are 6-sided, it's not a critical choice. If you pick the number of 1s or the number of 2s or anything like that, it's no big deal. And even if you use different numbers, luckily, it didn't matter either. So you got lucky. And it says, I don't have my stylus set up here to explain why I would expect that. So I'll pause the video at some point and make sure I got it straight, and then I'll restart and explain it to you. Okay, so let's see, what's the relationship between lambda and half-life? Solving, if you have time to spare, you can ask you. Who knows what time I have to spare, right? So 0.69, so lambda is equal to 0.693 divided by tau. Okay, and why is that? That's when right, that's the half-life, to find out what and so that means tau, the half-life, equals 0.693 over lambda. And they predict lambda be 0.1823, huh? So let's see, equals 0.693 divided by 0.1823 give us 3.8. Okay. What did we get? 0.693 divided by, we got 0.172. And I forgot to put the equal sign before it. Ooh, and we get 4, just as our other data predicted. Isn't that something else? Okay, so I'm going to pause this for a minute, get my tablet set up, and go back over what we just did a little bit more. Alright, so you wouldn't have noticed anything, but I'd been paused for a few minutes. So let's take a look at what we have here. So this original exponential equation comes up because the rate at which the number of decays we see depends on the number that are there. And that's a classic problem where you get this exponent, e to the minus lambda t. Now, we can also define things with this tau here. And the tau is called the half-life. And this is just something to do with exponents. And there may even be a typo right here. I think there's supposed to be an E here somewhere. But what we do is, if we set n equal to be 1/2 n sub 0, so then we have 1/2 n sub 0 equals n sub 0 e to the minus lambda t. Then we can see that the n sub zeros cancel out. And if we want to find out then a prediction for lambda, we can take the natural logarithm of both sides. And it turns out that the natural logarithm of 1/2 is 0.693. And so then the t of 1/2 becomes, and it's minus, and that's important because we need the minuses to cancel out. So the t of 1/2 equals 0.693 divided by lambda. So we can simply, if we define the time of a half-life, tau, so that means that we say minus 0.693 times t over lambda, t over tau. You'll notice that if now this is the t 1/2, which we say now is tau. And if we plug that in, we get back our negative lambda t, the original equation. It's just that people like to express it with tau. Now, we still have to find out what lambda is. And that's what the Phys equation gave us, is 0.172. And if we know what lambda is, then we can figure out what tau is, which we did up here. select. So 0.693 divided by the 0.172, and we ended up with 4.02, which is going to round to 4. And notice that, as I said earlier, let's see if I get a nice straight line here. Here we go. So here's my start point, 300, and then we make another line at the halfway point, which is basically 150 or 149, and then we make another line, but now we make it vertical, and we see that we decay down to halfway when we get to 4. Pretty nifty, huh? And in principle, we get it here. Let's see, it's 65 is the y-intercept here, so that means the 3250, which is about 3 to 4. It's not quite as clear cut. Okay, I think we've gone through it. I haven't explained why it's 0.1823, but I'll just make another video for that. If you choose a different dice number, well, I've said it in there. Let's see. Oh, these are the things that are supposed to be in the final logbook. Okay, so you would have the table. You'd have an explanation of the table. You have the graph here. These lines I put in are useful. And an explanation of what our lambda is. Oops. What our half-life is. Now yours, again, remember, yours is not going to be exactly the same as mine, I don't think. Might be close, but anyways, this graph needs labels for the axes and needs a title. And again, remember, for Mac users, you get the sidebar here when you double click the graph, but you don't get this drop down box. So your drop down box is when you go to chart tools up here, format, and that's where the drop down box is for you. Okay, good luck.